Good morning, everyone. I'm Anupallavi. Today, I'm going to present my project on UART protocol design using Verilog. Like UART stands for Universal Asynchronous Receiver. UART stands for Universal Asynchronous Receiver or Transmitter. It is a serial communication protocol where data is transmitted one bit at a time over a single line. During transmission, UART converts parallel data into serial data, and at receiver it will be back converted into serial data into parallel data. And UART is called asynchronous because there is no common clock shared between the communicating device. Instead, the baud rate is used for the timing control. This is the UART architecture. The first block is the clock gen or a clock generator. It generates a TX and RX clock. Then the UART transmitter block, which performs parallel to serial conversion, and the receiver block performs serial to parallel conversion. Finally, the top module initiates and connects all the modules together. UART frame format, that UART transmits data in the form of a frame. When there is no transmission, the ideal state remains zero. Then the frame starts with the start bit, which is always zero. Then the data bits are transmitted one by one, starting from the LSB, and the optional parity bit is transmitted for the error checking. Finally, one stop or two stop bits are transmitted, and the stop bits are always one. For example, here I have taken an example like hexadecimal A5. A5 is in binary is 10100101. UART transmits the LSB first, so we don't transmit this binary value from left to right. The first data bit is D0, which is one with including the start bit 0 1010. It will transmit one bit at a time. Then this UART design has a four main parts: the clock generator, UART transmitter, UART receiver, and a UART top module. And first, clock generator. The purpose of clock generator is to generate the separate TX and RX clock from the main system clock, and here the baud rate is given as an input and decides the based on the selected baud rate, and the different division values are selected for the transmitter and receiver. The RX clock is the RX clock will be faster than the receiver uses oversampling. The TX clock runs at the baud rate. This is the clock is the main system clock, reset signal, the baud rate selection, and the clock used for by transmitter, and the receiver clock used by the receiver. And the RX max and TX max are the counter values for the RX and TX clock. And the RX count and TX count are the counters used to generate RX and TX clock. And the in the if reset is begin the during the reset set, it is the default values are set. And these are the case statement. It selects the baud rate as the user selected. Then in the here, the counters are used to generate the actual RX and TX clock. For the every rising edge of the main clock, the counter is incremented. When the counter reaches its maximum value, it resets to zero, and the corresponding clock toggles. Same as for the TX clock generation. The RX clock counter has a smaller maximum value, so that the receiver clock toggle faster. And the receiver clock is 16 times the baud rate for oversampling, while the transmitter clock runs at the same baud rate. And the transmitter, the first the transmitter, the parallel bit data is stored into the data register, and then the FSM controls the transmission process. Then the start bit, which is 0, is transmitted. Then the data bits are transmitted one by one, starting from the LSP. If the parity is enabled, the parity bit is transmitted. After that, one stop or two stop bits are transmitted. Then the TX run is asserted to indicate the transmission is completed. This is your transmitter code. This is the first part. Like TX data. TX data is the input data has to be transmitted, and the TX register is used to store the data. Then the parity bit stores the calculated parity value. Then count keeps tracking the data bit being the transmitted. The transmitter uses an FSM with states ideal, start, data, parity, first stop, and second stop, and done. The parity generator calculates the parity depending on the selected baud rate, length, and the parity type. This is the second part, like FSM. This is initially the transmitter states in the ideal state. When the TX start becomes active, it moves to the start state and sends the zero. Then it enters the data state and sends the data bit one by one. Then the count value selects the current data bit from TX register. When all the data bits are transmitted, the FSM checks whether the parity is enabled. If parity is enabled, it sends the parity bit. Then it sends the stop bits or bits. Finally, it is done and enters the done state, and TX done becomes the one. Then the receiver performs the reverse operation of the transmitter. First, the data that it detects the start bit, which is 0. Then it samples the incoming serial data using the faster RX clock. Then the data are received one by one starting from the LSP. The received data are stored in the shift register. If the parity is enabled, the receiver checks the parity. It also checks the stop bits or bits. Finally, the receiver will be converted back into the parallel data, and RX done. It indicates that the reception is done. Code for UART receiver. This is first part. Um, this is data shift register. This is used to store the received data. Count is the sample counter. It counts from 0 to 15 because the receiver uses a 16 times oversampling. Bit count keeps track of the which data bit is currently being received. The receiver also uses the FSM state with for like ideal, start, receiving data, parity checking, stop checking, and done. This is second part of the receiver. The receiver continues for performing the received frame. In the received data state, it waits until the required number of data bits have been received. If the parity is enabled, it moves to the parity checking state. Otherwise, it directly goes to the first stop. Then, if two stop bits are selected, it also checks the second stop, and finally the receiver enters the done state. And here assigning the receiver data output, and here it clears the received output during the reset, and it shifts the received serial data bit into the data register. Top module, which connects all the three modules. It connects individual modules, clock generator, which has generated the transmitter and receiver clock. The transmitter uses a TX clock and produces a serial transmitter output. And the transmitter output is connected to the RX input through the TX RX signal. The receiver uses the RX clock to sample the serial data and produce the serial received parallel data. This is a complete UART system flow. This first 8-bit parallel data is given to the UART transmitter. The clock generator provides the received timing based on the selected baud rate. The transmitter converts the parallel data into the serial data and sends it in LSP first. The transmitted data contains the start bit, data bits, optional parity bit, and the stop bits. And the receiver detects the data contains same as it, and it samples the serial data using the receiver clock. If the parity is if it, did- this checks the parity and stop bits. If they are enabled, the serial data is converted back into the parallel data. Thank you.